Cache coherence in multiprocessor systems. Cache coherence is a mechanism that ensures all caches in a multiprocessor system have the most recent value of a shared memory location. This way, every processor sees a consistent value of the shared data. In a multiprocessor system, each processor has its own cache to store frequently used data from main memory. When a processor reads a shared variable, it may read the value directly from its cache instead of going to main memory. When a processor writes or updates a shared variable, the change must be propagated to the other caches using a write-update protocol. Alternatively, other caches may invalidate their copies using a write-invalidate protocol. These mechanisms ensure that all processors either see the updated value or fetch it from main memory. Cache coherence protocols handle this process automatically to prevent inconsistency in multiprocessor systems. Architecture with cache coherence. This diagram shows a multiprocessor system with cache coherence. At the top, we have the main memory, where the shared variable x is initially 10. Two processors, Processor 1 and Processor 2, each have their own cache, and both initially store x as 10. Processor 1 updates its cache value to 20, while Processor 2 updates its cache value to 30. With cache coherence, these updates are managed automatically so that all caches and main memory maintain a consistent value. The cache coherence block ensures that no processor sees stale or inconsistent data, keeping the system correct. Architecture without cache coherence. This diagram shows a multiprocessor system without cache coherence. At the top, the main memory stores the shared variable x with the initial value of 10. Two processors, Processor 1 and Processor 2, each have their own cache, also starting with x equal to 10. If Processor 1 or Processor 2 updates their cache, the change does not propagate to the other processor or to main memory. As a result, Processor 1 and Processor May 2 have different values of x, while main memory remains unchanged at 10. This inconsistency can lead to incorrect computation and unexpected behavior in multiprocessor systems. In a multiprocessor system, multiple processors such as CPU 1, CPU 2, and CPU 3 have private caches but share a common main memory. Initially, all processors load the same data item, called data X, from shared memory into their caches. When one processor updates data X in its local cache, the copy stored in other caches become inconsistent. The cache coherence mechanism detects this write operation. Based on the protocol used, the other cached copies are either invalidated or updated. On the next access, all processors fetch the latest value of data X, restoring data consistency across the system. Why cache coherence is needed? Multiprocessor systems use private caches to improve performance. As a result, the same memory block can exist in multiple caches at the same time. When one processor updates shared data, other caches may still hold old values. This leads to stale reads and inconsistent views of data. Such inconsistencies can cause incorrect program execution in parallel applications. Cache coherence ensures correct synchronization, reliable data sharing, and accurate results in parallel programs. Cache coherence requirements. A cache-coherent multiprocessor system must satisfy a few key requirements. First is write propagation. When a processor updates a shared memory location, the new value must eventually become visible to all other processors. Second is write serialization. All processors must observe write operations to the same memory location in a single, consistent order, even when multiple processors perform writes. Third is atomicity. A read operation must return either the entire old value or the entire new value, never a partially updated value. These guarantees are essential for correct synchronization, enabling reliable locks, barriers, and shared variables in parallel programs. Cache coherence mechanisms. 1. Snoopy bus mechanism. All caches are connected via a shared bus. Each cache controller continuously monitors, snoops, bus transactions. When a processor writes to a cache block, other caches invalidate or update their copies. Simple to implement but does not scale well due to bus contention. 2. Directory-based coherence. A directory maintains information about which caches hold each memory block. Before a cache block is modified, the directory coordinates, invalidations or updates to other caches, avoids broadcasting and scales better for large multiprocessor systems. Cache coherence protocols. MSI protocol. The MSI protocol stands for modified, shared, and invalid. In the modified state, the data is updated in the cache and the main memory is stale. In the shared state, the data is clean and may exist in multiple caches. In the invalid state, the cache block is not valid. When a processor writes to a block, other caches invalidate their copies. While MSI is simple, it can cause frequent bus traffic. Messy protocol. The messy protocol stands for modified, exclusive, shared, and invalid. The exclusive state means only one cache holds the block, and it matches main memory. The other states are the same as in MSI. Messy avoids unnecessary invalidations, improving bus efficiency. Because of this, it is widely used in modern CPUs, such as Intel processors. MOSI protocol. The MOSI protocol stands for modified, owned, shared, and invalid. The key addition is the owned state, where a cache holds the modified block and can supply it to other caches. This reduces the need to write data back to main memory. As a result, MOSI reduces memory writes and improves bandwidth utilization. MSI protocol. The MSI protocol stands for modified, owned, exclusive, shared, and invalid. It combines the features of messy with the owned state. MSI is considered one of the most advanced and widely used cache coherence protocols. In this protocol, modified data can be shared directly between caches without writing back to memory. This reduces memory traffic and improves scalability. Cache coherence in parallel and distributed systems. Parallel systems. In parallel systems, multiple processors share a common physical memory but have private caches. Cache coherence is handled by hardware-based protocols, ensuring all caches maintain consistent data. Issues like false sharing and write propagation are managed automatically by the coherence mechanism. Distributed systems. In distributed systems, there is no shared physical memory, and each node has its own local memory. Cache coherence is managed using software-based protocols, such as distributed shared memory. To maintain consistency, updates are propagated using message passing. Cache coherence provides several important advantages in multiprocessor systems. It ensures data consistency, meaning all processors always see the most recent value of shared data, which prevents errors caused by outdated information. By maintaining coherence, it guarantees correct program execution, avoiding problems that can occur when processors work with stale or inconsistent cached values. Another benefit is faster access, because processors can read data from their local cache while still maintaining the correct values, improving overall system performance. Cache coherence also supports fault isolation, helping to detect inconsistencies early, which simplifies debugging and error tracking in complex systems. Finally, it supports multiprocessing by making shared memory programming reliable and safe in systems with multiple processors. Cache coherence also has some disadvantages and limitations in multiprocessor systems. One major issue is complexity, because implementing cache coherence protocols adds significant design and hardware complexity. Another drawback is performance overhead, since maintaining coherence through updates or invalidations requires extra communication between caches and main memory. Latency can also increase, as frequent updates or invalidations may slow down processor performance. Scalability issues arise in large multiprocessor systems, where managing coherence across many caches becomes difficult and expensive. Finally, cache coherence protocols can increase power consumption, because the extra messaging and cache operations use additional energy in the hardware. Cache coherence has several important applications in computer systems. In multiprocessor systems, where multiple CPUs share main memory, each CPU has its own cache. For example, when a variable X is updated on CPU 1, the change should immediately reflect on CPU 2. To achieve this, cache coherence protocols like MESI or MESI are used to maintain consistency. In multi-core processors, modern CPUs have multiple cores, each with their own L1 and L2 caches. Cache coherence ensures that cores working on the same data always see the correct value. In parallel and distributed computing, such as shared memory programming using OpenMP or CUDA on CPU, multiple threads may read and write shared data. Cache coherence ensures that threads do not operate on stale data, preventing race conditions and maintaining correct program behavior. Cache coherence is also important in database systems and transaction processing. Multi-core servers running database transactions benefit from cache coherence because it ensures consistent reads and writes to shared memory structures, such as buffers and indexes. In the operating system kernel, which often runs on multi-core systems and manages shared data structures like process tables and memory maps, coherent caches prevent inconsistencies in system state, improving stability and overall performance. In graphics and multimedia processing, GPUs and multimedia accelerators frequently share data with the CPU. Cache coherence is critical when the CPU updates texture or frame buffer data while the GPU reads it, ensuring the data remains correct and synchronized.